let me just mention this because there is a common misconception related to this. There's something called Rayleigh scattering. Rayleigh is somebody's last name. I think it's like that you spell his last name. And scattering, like hits and scatters. Okay, so not refraction. Refraction is different. This is like hits and okay. So there's something called Rayleigh scattering, and the amount, or the quantity or energy of energy scattered is proportional to the fourth power of the frequency of the light. So if you consider sunlight reaching Earth, right? You have red, orange, all the colors in the spectrum. If you consider sunlight, you have red light, right? You have green light, you got blue, you got violet, right? They're all coming in together, right? Which of those colors has the highest frequency? Frequency. Let me help you out a little bit. Oh. It was the other way. Which color has the lowest wavelength? You can see the colors and the values of the wavelengths. 400 nanometers for this end, 700 nanometers. So remember that the speed of a wave is the frequency times the wavelength. They all travel in vacuum at the same speed. So the shorter wavelength corresponds to the higher frequency. So the violet light, the violet blue end of the spectrum, is the high frequency. The red light is less frequency. The numbers are such that, like for red light, for example, the frequency you can say is like 4.5 times 10 to the 14 hertz. While for around there, it depends on the shade of red. And for violet, the frequency is on the order of 8 or so times 10 to the 14 hertz. So the violet light corresponds to more frequency. So when sunlight coming from the sun, right, you got all the colors in the visible spectrum all traveling at the same speed. When they enter the Earth atmosphere has a lot of, nitrogen molecules, oxygen molecules, carbon monoxide, carbon dioxide, stuff, right? Particles, dust particles, and so on. Right? And the amount of scattering goes as the fourth power of the frequency. So which of the colors scatters the most? In general, which of the colors would scatter the most?
The violet, because that's the highest frequency.
The violet, right? So if the sun is over here, for example, the light coming in like this, and there you are, but you look this way. Suppose you look that way. What's the color of the sky?
Blue.
And let's say it's not cloudy, right? So it's blue. Why not violet? So what happens is that we humans, our detectors are the eyes, right? And we are more sensitive to blue than to violet. So of the light coming in from the sun, the violet gets scattered the most. And then second, blue. But we're more sensitive than blue than to violet. So we see it as blue. So that's why the sky is blue. A lot of people say, oh, it's because the ocean is blue. No. Okay? But that's because when you look, if the sun is over there and you look over here, you're not looking at the sun. If the light is coming from here, it's because the light came from the sun, scattered, it scattered the most, scatter, then that's the one that's going to be coming to you. But what if you watch a sunset? What is the color of the sun, roughly, or during sunset? In that case, you're looking at the sun, right? In that case, you're looking in this path. So which color will scatter the most out of that path? Scatter out. So imagine you got the red, the blue, all the colors. Which one? Notice that when you look at the sunset, like the light traverses more of the atmosphere to get to your eyes. Because the sun is low in the sky, so it's troublesome. So then, which color gets scattered the most? Out of this path, because it gets scattered. Which color gets removed the most?
Violet.
The blue and the violet. And then what do you have left over by the time it gets to you?
Like red, orange.
The one that scatters the least, which is the red. So sunsets are red-orange, because orange is right next to red. So those are the colors that scatter the least, because you're looking directly at the sun. What you're looking at is the light that essentially didn't scatter out of all the white light that's coming to you. You're looking at the light that reaches you is the light that didn't scatter out of the original beam of the sunlight reaching your eyes. So you're looking at the light that scattered the least. Well, it's going to be the one with the lowest frequency, the red end of the spectrum, red, orange. But when you look during the day in the direction of the sky, right? Not in the direction of a cloud, right? But and then in that case, you're looking, the sun is here, you're looking at the light that's coming to you, it's scattered light. And the one that scattered the most were the violet and the blue. But we're more sensitive to the blue, so it's blue. Cool? Okay. Okay, so let's go back to, I'll make a comment about this, since one of the demos for Science Night involved polarization, something called polarization. And I'd just like to say something about that. Let's see, in chapter 32, no, I clicked on 33. I wanted to click on chapter 32. Chapter 32. I kind of showed, sort of like a description of the electric and magnetic fields associated with an electromagnetic wave. And in this picture, right, the direction of travel of the electromagnetic wave is to the right along the positive x-axis, so the wave is going that way. So like I take a laser pointer and I shoot a light that way. But electromagnetic waves traveling in vacuum, in air, they are transverse waves. So the electric and the magnetic fields that make up these electromagnetic waves are perpendicular to the direction that the wave travels. And we said at some point that the direction in which the wave travels is in the direction of a vector called the Poynting vector, and that's equal to E cross B, electric field crossing to the magnetic field, divided by some number having to do with vacuum. It's called the magnetic permeability of free space. So the electric field crossing to the magnetic field will tell you the direction in which the wave travels. Because this vector, which points in the direction that the wave travels, is the result of a cross product of these two vectors, then by definition, for any cross product, this vector has to be perpendicular to both of these. So the direction in which the wave travels has to be perpendicular to the electric field, and it has to be perpendicular to the magnetic field. So if the wave travels along the x-axis, the electric field and the magnetic fields have to be on the y-z plane. So in this picture over here, just in this picture, right, the electric field is along the y-axis. It's oscillating for one cycle. One cycle is up, down, and back over there. Half the time pointing up, half the time pointing down, and then another cycle. and then another cycle, right? Right? And the time for one cycle is the period of the wave. But this electric field is oscillating up, down, up, down. As it's oscillating up and down, magnetic field has to be perpendicular to the direction that the wave travels. So it turns out to be, when the electric field points up, the magnetic field points this way. So that E cross B points in the direction that the wave travels. So the magnetic field is pointing this way, this way, this way, this way. So when the electric field points, like in this case, up, down, well, along the y-axis, one says that this wave is polarized along the y direction. Being polarized in the y direction means that the electric field is oscillating along the y-axis. If the electric field of this wave were along the z-axis, then you say the polarization of the wave is along the z-axis. So the polarization of the wave tells you the direction along which the electric field is oscillating. So, and this particular wave, right, as the electric field travels, as the wave travels to the right in this picture, right, the wave travels that way. Let's say that's the x-axis, and the electric field is oscillating up, down, up, down, up, down. So the plane right, formed by the axis along which the electric field oscillates and the direction that the wave travels, this plane, right, that's called the plane of polarization. And if that plane, if the electric field is always up and down, up and down, up and down, right, then the light is linearly polarized. So you say the light is linearly polarized along the y-axis. So the plane would be, right, this would be the plane of polarization. The wave goes that way and the electric field oscillates up and down. And so it's said to be linearly polarized. There are electromagnetic waves where the wave travels that way and the electric field oscillates up and down, but as it does that, the electric field goes like, the wave goes that way. I'm going to try to mimic an electromagnetic wave with the electric field going that way, and the electric field goes up, down, but then it starts going like that, and then that way, and then that way. In other words, the electric field oscillates up, down, and then it starts to go at an angle, and then an angle, another angle, another angle. Right? And if it goes this way, if it has the same electric field amplitude this way as the electric field amplitude this way, what happens is that during a cycle, the electric field rotates through a circle. So you say that the light is circularly polarized. It could be right circularly polarized, it could be left circularly polarized. In that case, the plane of polarization is rotating. If it could be that the electric field is oscillating up and down, but then it's got an amplitude over here of whatever, but then by the time it gets over here, the amplitude is different. And so it traces an ellipse, like a semi-major axis and a semi-minor axis. So you say it's elliptically polarized. So anyway, there are linearly polarized light waves, circularly polarized light waves, elliptically polarized light waves. These sources over here, the emitters are not in unison with one another, so it's randomly polarized. Like the light coming in is like you got the electric field in all, different waves, right? And so then you say it's randomly polarized. Yes. So if you have like many emitters, and some of them emit, let's say, up and down, another one like this, another one like that, another one like that, and it's like the light that you get from an incandescent light bulb, for example, is just randomly polarized. You get a lot of electromagnetic waves, making up the beam that reaches you with electric fields that are oscillating in randomly different directions, all of them. So it's just randomly polarized. So I say this because of the language of, what do you mean by the polarization of a wave, right? It's just it's a way of saying something about the direction along which the electric field is oscillating. So what does that have to do with this? Chapter 33. So there are materials like a sheet that, like in this picture over here, you have like the one from chapter 32 that I just pulled up, right? The wave travels to the right, and the electric field oscillates up, down, up, down, up, down, so it's linearly polarized light. But if you have a source like a light bulb, that emits light randomly, then the electric field is like pointing in all directions, and you have different components, and various. So this is unpolarized light. Polarized light, unpolarized light. Now, there are polarizers, things that can polarize light. So, for example, suppose you have this crystal here, or this material, and the material is made up of molecules, atoms, that have the property that if the electric field comes in and the electric field is vertical, then the material will absorb very little of that energy. But if the electric field is horizontal, it will absorb a lot of that energy. So what happens if you have light coming in, for example, suppose light comes in and it's randomly polarized. So any one of these electric fields, you can say, oh, that can be resolved into a vertical component and a horizontal component. The horizontal component will be absorbed, while the vertical component is going to get transmitted. So for all of these electric fields that are randomly oriented over here, suppose you have incident light coming in that is unpolarized, randomly polarized, all of those vectors you can think of as being, it's a vector quantity with a vertical component and a horizontal component, either this way or that way, or the vertical component this way, it doesn't matter. So what will happen is that this material will selectively absorb the electric field components that are perpendicular to this transmission axis, or they also call it the polarizing axis. It's called the transmission axis because if the electric field is polarized along that axis, it'll go through. So notice what happens. You have unpolarized light coming in, and what do you have after going through the material? Polarized light. So therefore, you had unpolarized in the beginning, and then after going through this, after that light interacting with this, now you have polarized light. So this is a polarizer. Does it polarize the light?
What difference does it make if we see other of the lights?
If you send it what?
When we see those polarized versus unpolarized light, what's the difference?
When I see it,
it's like when you drive it at night and you see the ring around like the headlights and stuff. And when it's polarized, it's less concentrated and it doesn't scatter as much. So when you look at it, it's more of a concentrated light.
Is there any application for that?
for what?
Isn't it
For the,
polarized glasses?
Yeah, like polarized sunglasses.
Oh yeah. Yeah.
Your monitor's polarized.
Oh yeah. A lot of applications of polarizers. So I'll mention some as they, I mean, there's one that I can think of right away, but it deals with this topic called boosters angle reflection. But we haven't talked about that yet. Now, some people have how does it absorb it? How does it how does it absorb one component but not the other one? So let me just give you like an analogy. what if you have, these are usually found in some labs. There's a chunk of wood, more wood, and then you just connect this to, like imagine I take this ruler, actually they're like this. Imagine I cut this ruler in half, and I take that part and I put it here, and I have this one. So like I have two rulers. And then I just connect them with wires. Wires, metal wires. Wire, 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 wire. Oh, these are. Now, the wires are conducting metal, are conductors. So they're made up of atoms that have nuclei with electrons going around them. And in a metal, 1 or 2 electrons, sometimes 3, depending on the metal, but 1 roughly electron per atom is free to leave the atom. It can go hang out with its friends and do whatever it does, right? In a metal. And so, so you have this, they're called free electrons. Not because they don't cost any money, but because they have that freedom to leave the atom and, go hang out. So you got these free electrons here all over the metal, right? I mean, it looks like there are just a few, but there are zillions of them. One per atom, and that's a lot of atoms in there, right? In a solid. So if you send in, for example, an electromagnetic wave, and the electromagnetic wave is vertically polarized with the electric field oscillating up and down, right? Then what will happen when the electric field oscillates up and down? Well, you learn for those of you who have taken Physics 280, that the electrical force, external charge by an electric field is given by this. And the electrons are negatively charged particles, so they're negative. So this is electric charge, which is a scalar quantity. Just think of it as a, whatever, it's a scalar quantity. Electric field is a vector quantity. So if at the instant that the electric field in this wave points up, the free electrons are driven down the wire because the force is in the opposite direction, right? And at the instant that the electric field, because the electric fields are up, down, up, at the instant the electric field points down, I'm just going to use another one over here. When the electric field points down, those electrons are going to be driven up. So what happens is that as you send in this electromagnetic wave with the electric field polarized vertically, right? The free electrons in these wires are driven by the electric field like up, down, up, down, up, down, up, down, up, down. And so they're driven by this electric field, so that's energy that the electrons are getting from the wave. So that this unit absorbs a lot of that electromagnetic wave going through this unit. And usually this is done with like microwaves, given the dimensions and so on. But something like this it could be thought of as a polarizer. If the electric field of the microwaves is vertical, up, down, up, down, up, down, then a lot of these electrons will respond. They'll be driven up and down by the oscillating electric fields. And the fact that the electrons are driven up and down, they're getting energy from the field, so energy is being absorbed from the field. So you get less energy on the other side than you had coming in. Now, what if instead you sent in microwaves towards this unit, with wires, but the electric field is oscillating this way, right, left, right, left, right, left. So if they oscillate right, left, right, left, right, left, when the electric field points to the right, the force on the electrons will be to the left. And when the electric field points to the left, the force on the electrons is going to be to the right. But what happens over here is that the electrons want to go right, left, but these are thin wires. There isn't room for them to go right, left, right, left. So therefore they don't end up being driven right and left because they're confined to the wire, and so less energy from the wave is absorbed by the electrons. And so if the electromagnetic wave coming in is polarized horizontally, in that case perpendicular to these wires, then it'll go right through with very little absorption of the energy by this unit. So in that case, you could say that the transmission axis of this unit is horizontal. that means that if the electric field comes in horizontally, oscillating horizontally, only just a little bit of energy is going to be absorbed by this unit. Most of the energy is going to go through. But if the electric field comes in vertically polarized, then this unit is going to absorb a lot. So this unit selectively absorbs the components of the electric fields that are vertical, because what happens if I send in an electromagnetic wave and the electric field oscillates at an angle, like this way, that way, right? So if it comes in at an angle, then I can resolve that electric field into a component parallel to the transmission axis, which is going to go through, and another component perpendicular to the transmission axis, which will drive electrons up and down, which is going to get absorbed. So this unit will, if you have randomly polarized electromagnetic waves, and by the time it goes on the other side, you get microwaves, electromagnetic waves that are horizontally polarized. So you can think of this as a polarizer. And the same thing happens in, with if you have light over here, visible light, depending on the arrangement of molecules over here and so on, they can selectively absorb one component of the electric field and let the other ones go through. So it's called a polarizer. Was it he who asked the question about, no, was it you, the applications? So, just to say something about that, in lasers, for example, all lasers have a reflecting mirror. Usually they reflect about 100% of the light that hits it. It's a chunk of glass. You have what's called a gain medium. A gain medium. That's the thing that lases. We'll talk about lasers later on in the course. Yeah, there's actually a verb, it lases. And then you have another mirror over here. It's called the output coupler. But this one has a reflectivity on the order of 95%, 90%, 88%, around 90%. And this medium is composed of atoms or molecules. This medium could be a solid. It could be like, the lasing medium in my laser pointer is a solid, so crystal. It could be a liquid. For example, the YAG, sorry, not the YAG laser, the dye laser. It's the medium that creates the laser light it's a dye liquid that it's made to flow with a pump. And it could also be a gas. This could also be a gas. Like the helium neon laser, the carbon dioxide laser, the argon ion laser, excimer. There are just various gases that can be used as a gain medium for lasers. And then here's another mirror, right? That's 95% reflecting. So what you need to do is excite this medium. And so there has to be an excitation source. So you have to dump energy in there, And then the excitation source could be, an electric current. For example, in this case, it's an electric current. There's a battery in there that produces a current. It collides with the atoms, excite them to higher energy levels, and then we'll talk about how the actual process happens later on in the course. But it could be an electric current. In the argon ion laser, the unit is like this long, like 1.5 meters in length, and then you pass just a big current right through this tube with argon ion gas in there. And electrons going through that gas, boom, 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 collide with the argon ion, atoms, and excite them to higher energy levels, and so on, right? This another source of to excite this medium is just like a flash lamp, like in the Ruby laser or the Yak laser. You just a big flash of light, and then send in a whole bunch of photons, and then the atoms over here absorb the energy, get excited, and then the lasing process happens. Sometimes you use another laser. You shoot a laser, you focus a laser into this medium, so you can use a laser beam as an excitation source. So you use a laser to drive another laser, right? And for example, the Yak laser can be used to excite the dye laser. The output of our argon ion laser can be focused in here. If this is a titanium sapphire crystal, titanium sapphire laser, then you use the output of a laser to get another laser going. Okay, so there are various these things. So in the case, for example, of the titanium sapphire laser and the dye laser, there are other components in here, and sometimes you put like a pair of prisms over here, positioned in a particular way. Right? So the light, this thing lasers, it makes up light, and it goes here. You want all the light to get reflected, right? And then it comes here, and then when it goes through this medium, that light gets amplified. And it gets amplified, and then you can, with these prisms over here, if you orient them at the right angle, right, you can minimize the reflection, and you can, or introduce a loss. You can set the light to be lost, and then, but the idea of the laser is for the light to go this way, then hit over here, and then, well, if it reflects 95% of the energy, 5% of the energy is going to go through. This is your laser output. This whole thing is the laser cavity. And so the rest of the energy goes back, and it goes like this. It gets amplified, and then boom. So these prisms over here are used to control the length, the duration, not the length, well, yeah, the duration of the laser pulse. So you can set these prisms, and you can cause them to reflect light for a certain time, and so then you have no light, but then in the meantime, this is getting more excited, gaining energy. So, and then at the right time, you can insert these prisms, for example, and then the light that goes in here will be transmitted over here if it comes in at the right angle, and then so if you figure out the time that it takes the light to make this trip and come back, and every time the light gets over here, you let it through, but the rest of the time you get rid of it, then the light will get amplified. And only when the light, when this is oriented correctly, this will go through, and then you get a pulse light coming out, and you're gonna get a pulse. So the timing between these pulses, it's how long it takes the light to go to the other side and come back. Right? So it's like the light is going back and forth, boom, 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 continuously, right? But then you introduce a loss so that the thing doesn't laze. It's like less energy is being made over here than. Well, anyway. So the point is that you can use these reflections, and the light has to be polarized in a particular direction for this process to work. So I'll probably say something about the Brewster's angle. This thing has to be put in, they're called Brewster prisms. So, and then the output, the light is going to come out polarized in a particular direction. Right? It's usually vertical. You can take some of these pulses of light over here, for example, and then you can pass it through some crystals. This is called, for example, a second harmonic crystal, which does something really cute. You have light coming in of a certain frequency or certain wavelength, and then the light comes in, right? There's an interaction over here. It's a nonlinear interaction between the crystal and the light. And what happens is that you get twice the frequency of the light, which means half the wavelength of the light. It's called the second harmonic generator because you come in, this is like the fundamental frequency, and then this is the second harmonic. So for the YAG laser, for example, for that laser, the wavelength of the light that comes out is 1054 nanometers. It's in the infrared, near infrared, so you don't see that. But then you pass that radiation, the visible is from 400 to 700 roughly. You pass it through the second harmonic crystal, and then you have this beautiful green beam over here. Because half of that is what? 1064. 532 nanometers, and that's in the green. So depending on your application, what's the wavelength of laser light that you need, you can use this unit. So, the controlling the polarization of a light is used a lot to make a lot of these fancy lasers work, especially in creating pulsed lasers. The YAG laser, for example, it's a continuous wave laser. You're putting in energy all the time. The light is coming out all the time. But then the output of this other laser, why would you need a laser to drive another laser? This one sends light all the time, while this one, if you drive this other laser, then you can get a pulsed laser. And then, controlling the direction in which the electric field of the electromagnetic wave that oscillates back and forth in this cavity, right, is oriented, can allow you to introduce losses, or depending on the orientation, minimize losses also. And then, there are various applications like that in this field of laser optics.